morning. So the subject code is CEC358. Subject is underwater imaging systems and image processing. So under this we are seeing about unit 2, optical image processing. So in the last video we had discussed about how the digital image is formed and how we are measuring the quality of the digital image and what are all the process involved and how the image can be geometrically transformed, that is rotated, zooming, every observation we are discussed. So now in this video we are going to see about image reconstruction, spatial filtering, histogram and binary image. Let us see one by one. So first let us start with image reconstruction. So what is this? So image reconstruction, the foundation for it is we are taking the projections straightforwardly and we are explained it intuitively. So for example, consider this image. So I am taken from the book directly so that you will be more clear when you are referring that book also. So you can also use that Gonzalez book. So in that it is given like this figure. So when you see this image, to give the physical meaning, so let us assume that this region is a slice. We are slicing the image through a section of a human body which showing a tumor. Take this example. So in order to study the reconstruction, let us study with an example. So and embedded in a homogeneous area of tissue, that is considered to be the black background. So that tissue will be black background and the tumor cells will be bright in color. So consider that image. Such a region must be obtained by passing a thin flat beam of X-rays perpendicular to the body and recording at the opposite end measurements. So we can get such a region by passing this process, that is X-rays. So that is proportional to the end measurements are directly proportional to the absorption of the beam as it passes through the body. So how much amount of light is incident on that particular tissue and how much it is absorbed and how much it is reflected back. So depends upon that absorption property we get that final image. So the tumor absorbs more of the X-rays, so it looks black, hence giving a higher reading for absorption as the signal on, that is the absorption profile that we can see. So now see this figure. So it gives the absorption profile. So this first A figure, it represents the flat region with the object parallel to the beam and detector strip, and this is the absorption profile. So here on the top you see, so we have so many absorption profile. And what is the B image represents? It represents the back projection of the absorption profile. And C represents the beam and the detector strip which are rotated. This beam, you see this beam and this detector strip are rotated 90 degree. And this D represents this second figure, no, B figure. So while you rotate that B figure, so that you get a D, back absorption of the absorption profile. And what is the E figure? Sum of A and B, these two figures. So okay, these two figures if you add, you get this sum of B and D. Okay, that is resulting of adding another back projection at 945 degree. So result of adding yet another back projection, this is 135 degree, and this last figure, it represents results of adding 32 back projections. So what is this actually? So this process is image reconstruction. So we are creating one back projection of the absorption profile. That is the first step. We have to take an image and we have to get the back projection absorption profile of that particular image. First step, you have to get an absorption profile and you have to back project that absorption profile and you have to rotate and get the back projection. So rotate the image and get the back absorption profile of that image, and finally adding all the absorption profile, we get the reconstructed image. So observe that maximum absorption occurs through the center of the region where the beam encounters the longest path through the tumor. So at this point, the absorption profile is all the information we have to about the object. There is no way of determining from a single projection. If you take a single projection, we won't get anything. So we are dealing with a single object or multiple objects along the path of the beam, but we have to start the reconstruction based on this partial information. So in the second figure we see we are projecting the absorption profile back along the direction of the original beam. So in the figure, So we will see now this process is called back projection. It generates a 2D digital image from a 1D absorption profile waveform. Suppose next third figure na, this C figure. So what is this C figure? It represents that when we rotate the beam or the detector arrangement by 90 degree and then repeat the back projection process. And what is this D figure? We are adding the back projection. So we get that E. So now how the intensity of the region containing the object is twice the intensity of the other major components in the image. So now you see the image, E image. So okay, A, B, C, D, E. So what is this E image? It contains the intensity. So many intensities. Now this horizontal line, vertical line, center area. So we have, while we have this, so we have more, that is E figure. Intensity is twice the intensity of the other major components of the image. So it is intuitive that we should be able to refine the preceding results by generating more and more back projections at different angles, and finally we have to add it together. So as the number of back projections increases, the area with greater absorption gains in strength relatively to the homogeneous areas in the original region, until those areas fade into the background as the image is scaled for display, which we are obtaining. Final image, if you see, we are getting 32 back projections. This last image, it is the result of adding 32 back projections. So that is, by taking more and more, we are getting more strength. The absorption results will be more. So based on this discussion, we can say we can have a set of 1D projections, and the angles at which those projections are taken, angles also taken, and the basic problem in tomography. This is best used. This reconstruction, it is best can be understood when we take the tomography, computer tomography, so that it will be very clear. It is tomography, it is to reconstruct an image of the area from which the projections are generated. So in practice, we are taking numerous slices by taking the translating an object perpendicular to the detecting part. Stacking. Next, first we have to take numerous slices, then we have to stack the slices so that we get a 3D rendition of the inside object. So next, in the figure also it shows the rough approximation can be obtained by using a simple back projections. The results are too blurred. You see the image, H image. So what this H image? So okay, it is so blurred. Okay. So it is so blurred in general to be of practical use. So thus the tomography problem also encompasses techniques for reducing the blurring inherent in the black projection process. That is the drawback. We get a high absorption strength, but we get the blurring also. So for this, what are all the tools can be used? Mathematical foundation for this reconstructions are radon transform, inverse radon transform, and the projection slice theorem. And we are all, these are all mathematical foundation, and we are also having computational techniques, which includes filtered back projection and a variety of intuitive iterative methods. So there are several geometries also commonly used, including parallel beam, fan beam, cone beam. Next, there is a popular algorithms also, Shep Logan phantom image. It is to evaluate the different reconstruction algorithms. The effective approach is to perform a reconstruction includes several methods in a technical computing environment for data analysis, visualization. So everywhere we are popularly using this reconstruction, and in our syllabus we are going to study one on mathematical foundation, radon transform, and another one is the filtered back projection. These are given in our book also. So first is parallel beam projection is in the radon transform. So it is done by John Radon, and it was developed in the year 1917. So he is a mathematician from Vienna. So here deriving this expressions for projecting the 2D object along the parallel rays as a part in the line integrals. So he rediscovered after 4 decades. So it is also rediscovered in England and United States. So let us consider a Cartesian coordinates. So what is this radon transform? So we are taking a straight line in the Cartesian coordinates, and it can be described either by its slope intercept form, that is y equal to ax plus b, as shown in this figure. The projection of a parallel ray beam can be modeled by a set of such lines as it shows. An arbitrary point in the projection profile at coordinates. You take this point rho j comma theta k. It is shown in the figure also. So it's a ray sum of the line x cos theta k plus y sin theta k, which is equal to rho j. So these are the mathematical foundations. So this is the geometry of a parallel ray beam and its corresponding projection. So how it is projected and what are all these values. So okay, complete projection, it is represented by g of rho of theta comma k. So we are taking that rho of theta comma k, and that final expression is also given as an integral format. So this expression we are using, and for the above thing can be used for shifting property of the impulse signal delta. Okay, so the right side, this equation, it represents the preceding equation is 0. Okay, so and this next equation we are considering all the values of rho and theta. So the generalized form can be written like this. So this expression which gives the projection of f of x comma y along an arbitrary line in the xy plane, and this is called the radon transform. As this figure shows, the g of is called the, by inserting theta k is the radon transform. So the approximation can be written like this. So by the values of these two parameters. So these are the things we are that is mainly we are projecting with theta k. Okay, g of rho comma theta we are projecting, and this is the mathematical formula behind this back projection, parallel beams with radon transform. So finally the back projected images are like this. So from this area, that is from 0 to pi and pi to 2 pi we are taking, and finally summing up all the transforms we are getting the all the, that is all the back projections, we get a good absorption gain strength. Next, the computational methods include the filtered back projections. Let us see that what is this Fourier slice theorem and what is this filtered back projection. So far the mathematical method we have discussed, that is radon transform. They are taken a single line with theta, rho and theta. They are projecting to that parameters and they are mapping. So okay, that formula we have discussed, and finally we are collecting all the back projections and we are summing up. So here also in filtered back projections we are also taking that g of rho comma theta, that is 1D Fourier transform, and it is given like this in this expression. So this is the first expression, capital G of omega comma theta. This expression is for a fixed value of theta. This is the result in the computed tomography, and we call this expression to be the Fourier slice theorem, which states that Fourier transform of a projection capital G of omega comma theta is a slice of the 2D transform of the region from which the projection was obtained. That is, G of omega comma theta is equal to f of u comma v. So for as usual we have, this is the 2D Fourier transform that we also know. Now let us see how it is in the graphical format. So this is the Fourier slice theorem, and these are all the equations here we are using. And if you go through this, we can understand this theorem. That is, we are taking all the back projections and we are slices. So okay, all the slices are stacked together, and finally we are summing up and to get the image, final reconstructed the image. So these are all the derivations we are having in this Fourier slice theorem, and these are all the simple steps to be followed, and it is given like an algorithm format, and it is best understand, it is easy to understand what are all the steps we are taking, and by summarizing all these we can get easily the reconstructed image. So where it is actually used, it is used to create a 2D or 3D effects. No, we used to have 3D effects also, 3D cinemas also we are using watching. So there we can use this projection method, reconstruction method. So these reconstruction techniques forms the basis of common imaging modalities, such as mainly it is used in tomography that we see na. So that is computed tomography, CT, MRI scans, PET, and they are useful in medicine, biology. So these are all the applications of image reconstruction. So next we will move on to the spatial filtering. We know spatial filtering, it contains smoothening filters, sharpening filters, and Laplacian filters. So actually this filters, spatial filtering is an image enhancement technique. What is this image enhancement? It is to improve the brightness, contrast, and appearance of images. Next, what are all the techniques usually we have? It has spatial filtering, another one is frequency filtering. In spatial filtering we have smoothening and sharpening, and in frequency filtering also we have smoothening and sharpening. So what is a filter actually? It is a process that removes some unwanted components or small details in an image. So as we are using a T filter also in our house now, so it filters out something and it removes the unwanted things. So okay, the needed will be passed out of the filter and the unwanted things will be settled inside the filter itself. So similarly here also we have two types, one is spatial domain filters, another one is the frequency domain filters. So what is the spatial filter? In general, in mathematical we are having one 3 cross 3 array like structure, that is we are calling this as a filter, or we can also call it as a mask. So and this contains some values, we are having this 3 cross 3 or 5 cross 5 anything, but we have to rotate all over the image at all points in the image, and we are doing some mathematical operation with this mask value and the intensity value present in the image. So thereby we are changing the intensity values, thus the image quality will be improved. So we are calling that as an enhanced image. So what is the approaches of spatial filtering? It contains two steps. First is a neighborhood, that is a small rectangle we are forming. A filter contains a small rectangle. So nearest pixels, the neighbors pixels will also there in that rectangle, and a predefined operation that I told you now, it contains some value and we are doing some operations with the original values, intensity values in the image also. So some predefined operation will be performed, and filtering creates a new pixel value replaced by the old pixel value. So in spatial filtering we are also called it as a spatial mask, kernels, we can also call it as templates windows. Okay, so this filter, if the filtering, it creates a new pixel values with the coordinates equal to the center of the neighborhood. If the operation is linear, we are performing some predefined operation na. So if that operation is linear, then we call that filter to be linear filter, otherwise it is non-linear. So how is actually, so they take, this is the image and this is the image origin, this is and we are placing that mask na, that filter, it is moving from each pixel to pixel, and by placing on the above the image, some predefined operation will be performed with the filter values with the original values in the image itself. So thereby the intensity values gets altered. So that new intensity values gives a better vision to the viewer. Here we are the testers. So okay, human eye is the process. We can judge whether it is enhanced or not. Our eye gives the better results. So for that we are also using correlation and convolution process. It is the process of moving a filter mask over the image and computing the sum of the products at each location. So in order to have a move the filter mask, we are having this correlation process. So here in convolution process it is as same as the correlation, but here the filter is first rotated by 180 degree. Next we will see about spatial filter. So first we will see whether the predefined operation is linear, then we call it as linear, otherwise non-linear. So first let us see about linear filters. So okay, if it is smoothening filters, then we can also call it as low pass filter or average filter. So this low pass filter, what is the result? It reduced sharp transition in the intensities. So for example, if you take all the pixels in the neighbor are of same value, but one pixel is of a unique value, very different value, so then we can call that as a sharp transition, that will be reduced by using this filter. So what it actually, since it is averaging filter, we are taking the average of all the intensity values and we are changing the center value by the average value. So it reduces, by using this filter we can reduce the sharp transition. Then random noise is an example for sharp transition. So that noise will also be removed by using this average filter. And we can also use the edges that are characterized by the sharp intensity transitions. So what are all the other sharp transitions? Means edges are also having sharp transitions, that will also be characterized. So by using this averaging filters, but generally it will produce blur effects, blur edges. So if all the coefficients are equal in the filter, then we call that filter to be a box filter. Next one we'll see about the weighted average filter. So it is also a linear filter. So if it is average, then we can call it as a smoothening filter. Okay. So its pixels are multiplied by the different coefficient. Weighted means multiplied by different coefficient. The center point will have more weightage than any other points. So we can call this as a weighted averaging filter. So why we are using this filter? It will reduce some blurring in the smoothening process. It removes. So and intensity of the smaller objects blends with the background. So it looks as same as the background. So this is the smoothening linear filter. So this second one represents the weighted filter. So okay, since the center value has the more value than the other of rest of its neighbors, so it is called weighted average filter. So by using this filter, how the image looks? So okay, so this is the image you see here. So it includes, since it is a low pass filter, it reduces all the sharp transitions. So we get more blurring effect by using this smoothening filter. So first is the image filter, and all the rest of the image represents the smoothening filter with mask sizes. Okay, if you use 3 cross 3, it is more good, but if you use 35 cross 35. Okay, this B image, it uses a filter mask of 3 cross 3. Okay, array size of 3 cross 3, it looks good, little blurring. But if you use 35 cross 35 mask, so it gives more blurring effect. So okay, according to the application, we can use this mask size. Okay, similarly it is for next example it is given. So and this binary image, this gives only two intensity levels. There is no gray shades only we will have white and black color. So that is our binary image, result of thresholding process. Either you have to put it to black, either you have to put it to the white color. So you have only, that is the binary image. So next we will see the non-linear filters. So in linear filters we see about the averaging filters, weighted average filters and box filters. But in non-linear filter, here we are taking the ranking of the pixels. So you have to arrange the intensity values either ascending or descending order, and if you take the median value and replace it with the center value of the pixel, then it is median filter. And this median filter is used to remove the salt and pepper noise. What is the salt and pepper noise? Salt means it is a white color. So white represents the maximum intensity 255, and black, pepper looks black color. Black gives the intensity value 0. So that will be removed. Since we are replacing it with a median value, all the zeros and ones will be, maximum values will be removed, and it is replaced with a median value. So it is used to remove the salt and pepper noise. Also we can use a median filter as the 50th percentile, or it is a 100th percentile or 0th percentile. If you use the maximum value replaced with the center value, then we can call it as a max filter. If the center value is replaced by black color 0 value, then we can call that to be a minimum filter. So what is the result of using median filter? Seeing the image, we can what is the grains, that extra white grains, all it will be removed because it is replaced with the median value. So that is the noise reduction. So the image A is the original image, X-ray image. It is most corrupted by the salt and pepper noise. And this B image we are using 3 cross 3 mask, and this is averaging mask. Before that linear filter we are studying, so by using that, the result will be like this. But if we use a noise reduction with a median filter, it is more good. Similarly, it is the next image. So next we will see about the sharpening. First, so far we have discussed about smoothening filters. So smoothening filters produces blur effects. But here, and it removes all the sharp edges. But here the name itself, it is very clear, it is sharpening filters. So the result will be sharp edges and fine details in the image will be very clear. So and it removes all the discontinuities, noises and slowly varying intensities. Everything will be removed here. So here we are going to find out the differentiation. So far we have in averaging we are summing up. So it is integration, but here we are going to find out the difference. What is the neighboring pixel and how far it is differed. That means sharp details can be enhanced. So what is this foundation? In order to find the differentiation, differ from the neighboring pixel. So there are two types of differentiation. One is the first order derivative and second order, two times difference. If you are finding with the two times difference between two pixels, then it means second order derivative. If you are finding the pixel value difference with one set of neighboring location, then it is called a first order derivative. So and there will be some rules for that. If the difference value that should be 0 in the areas of constant intensity, so all these conditions should be followed. So okay, and the second condition, it must be non-zero at the onset of the intensity ramp or step, and it must be non-zero along the ramps. So first order derivative, if you see this, you can find out. Okay, so this is the first order derivative. So first line, this is a scan line, and these are all the scan line. What it represents? 666. What it represents? So the intensity values here, it is 666, and slowly the intensity value is goes the ramp edge. You note the curve, it is ramp, and here it is 5 4, like this it is getting down 5 4 3 2, and here it is constant intensity, and again here it is a random change, so 666. So first derivative means you have to subtract, okay, from this the neighboring values, the next pixel you have to subtract along the scan lines, and second derivative means you have to difference two times, so that you can observe from this figure also. And we are plotting the same intensity in the below. So okay, that dots represents, only black dots represents the first derivative, and the square boxes represents the second derivative. So by doing such a operation, we can get a fine details in the image, or we can call this differentiation, first derivative second derivative process, to be the sharpening filters. So always we call this second derivatives to be Laplacian. Two times we are taking difference. So what is this? Pixel location. For example, if you take x comma y is the pixel location, x plus 1 comma neighboring pixel, the next location it is x plus 1 comma y, and the left side, the next this side neighbor, left side neighbor will be x minus 1 comma y. Okay, and you have to find the difference from this pixel and this pixel, so it is minus 2 of x comma y. Similarly for the y location, so if the above pixel, for your current pixel, if you are considering to be x comma y, and the above pixel will be x comma y plus 1, and the below pixel will be considered as x comma y minus 1, and you are finding two times difference, and finally summing up you will be getting the second derivatives. So the mask will be like this. In order to have a two times differentiation, the mask will be like this. So it is diagonal terms. So these are the mask for diagonal terms, everything. So and it can be represented like this. So if the center coefficient of the Laplacian mask is negative, then the function will be like this. If it is positive, it is like this. So sharpening effects. So after applying the pixel, how it will be? So first input image, A image, this top one, it represents the blurred image, and second one is Laplacian image, that is first order difference, and the second one is Laplacian with scaling also we are doing. Next D image, it represents the sharpened image. Okay, so we get the fine details. You see the moon, the surface of the moon, all the dots we are clearly seen. And finally is the result of using the mask. So this mask, this B mask, by using this B mask we get a more sharpened image. So okay, that we can see it visibly. And this is next topic we are going to see about unsharp masking or high boost filtering. So okay, for example, if you take this is the original image, what is this? So first represents A, second represents B, C, D. Okay, the graph also A, B, C, D. First represents the original signal, and second one is the, actually this is the intensity range. Okay, so we are plotting the intensity range in the form of graph. So next one is the blurred signal with the original dashed. So this is a, this dashed represents the dashed lines represents the original signal, but this blurred signal has a represented by the solid lines. So next what we are doing, we are third process we are doing unsharping. So actually we are subtracting these two. So what is the difference between the original image and the blurred image? So that details alone we are extracting. Okay, how much amount of blurring how it differences from the original image that we are obtaining, that is unsharp we are obtaining. Next, lastly is called the sharpened image. So in the original image we are placing that unsharp mask, so we get the sharpened image. We are not subtracting any details, we are additionally adding that blurred details, that details to the original image. So simply, what are the steps to be followed? Read the original image f of x comma y. Blurred original image can be considered as f dash of x comma y. So now we are using the mask, that is you are subtracting the original image minus the blurred image. So here that is the unsharp mask. Now original image minus blurred image, you get this unsharp mask. That is the third step. And finally you are adding that mask to the original image. So this is your mask and you are adding this mask to the original image, so you get a sharpened image. So this is the steps for unsharp masking. And what is this high boost filtering? So the same steps, you have to take the original image, you have to take the blurred image, next you have to find out the mask as same, but here you are adding some coefficient with the mask, so it is high boost filtering, more sharpened image. So result of high boost filtering you see here in the E image. So first image is A, B, C, D, E. So last is the result of high boost filtering, and before that is the unsharp masking, result of using unsharp masking. Okay, so we had the more sharpened image with the help of high boost filtering. So here also the first derivative, how to find out, if you find a single difference with the x and y coordinates, then it is called gradient operator. If you are finding 2 times the difference, then it is called Laplacian operator. So this gradient is represented by gx, gy, and what is the magnitude of this value? Square root of gx square plus gy square, and this is your del f. Okay. And what are the mask, different mask available? So this A represents the 3 cross 3 image. Okay. Now this B and C represents the Robert cross gradient operator, and this last 2 figures, below 2 figures are there na, D and E, these are called as Sobel operators. So here if you add all the mask coefficients, you get 0. So that is it represents the derivative operator. So by using the Sobel operator, how it is how the image looks like, that is the example for this, and this is for Laplacian. Okay, the second represents the Laplacian. First is the image, and this C represents sharpened image by adding A and B. Okay, by using A, adding A and this B image, we get third image as sharpened image, and fourth image is the Sobel gradient, that is difference operator. Gradient we will studied na. So gradient means single difference. This is the gradient operator. So this difference operator is actually defined as a Sobel mask here, and we are applying the Sobel mask, we get the output like this. So okay, it's sharpened edges. The first image you see and the last image you see, you can find out the difference. It has more sharpened edges. Similarly, this is a second example, you can go through this. Next we will see about what is histogram. So histogram is nothing but collecting the different values of intensities present in an image. So that is the simple definition. So here it is with the different intensity values in the range 0 to L minus 1, and it is having a discrete function h of Rk, which is equal to Nk, where Rk is the kth intensity value and Nk is the number of pixels in the image with the intensity Rk. So what is this normalized in histogram? So we are minimizing to a smaller value. In order to have a smaller digit, we are dividing with the total number of pixels, that is product of rows and columns. Mn is product of rows and columns. So that we will have a range with 0 to 1, that is normalized histogram. Why we are using this histogram? Why this information intensity values? So it is good to have the enhancement effect. So information inherent in histogram is quite useful in another image processing applications also. So okay, this histogram is also used in image compression as well as in segmentation. So what is this equalization process? So in histogram itself we have 2 types of enhancement. From the histogram information we can do enhancement in 2 different ways, and first one is image histogram equalization, and second one is histogram matching. So these are all the steps, basic conditions to have a histogram equalization. So here we are taking one image and we are mapping all the intensity values by using one transformation function. So here T of R is a transformation function. What are all the conditions for transformation function that is given here, and we are using that conditions and using a transformation function. And here what we are doing, and we are mapping values to the another plane. So by using the T of R, so single values to the, so by using the transformation function to be like this. So that is monotonically increasing function. It should showing multiple values mapped to a single value. So here we have multiple values and it is mapped to a single value. But in B figure, here 1-to-1 mapping. One intensity value is mapped to a single intensity value. So this x-axis represents the original image intensity values, and this value is transformed image intensity value. This SK represents the new intensity value. So this is our histogram processing. So actually we are mapping to a single value, so there no repetitions of values will be there. So the image looks quite good by using this histogram equalization. What it means, we are replacing the some of the few intensities in the image with the other values. So what is this other value? That is determined by the transformation function. So that is histogram. So in the equalization we have so many steps, but it is very simple itself. So here it is the random variables. All the intensity levels are in the range of 0 to L-1, and usually we know if it is intensity values are random in nature. For any random discussion we have to take the help of probability theory. So because it is uncertain, the intensity level appear in the image is uncertain, so we are going to with the help of probability. So here also the random variable we are taking as probability density function. So R represents the gray values present in the original image, and S represents the gray values present in the transformed image. So let us collect two different PDFs. One is PS of S, another one is PR. Okay, so PR of R. So okay, that is the original probability density function, and here we are finding the differentiation dr with respect to ds, differentiate the original image with respect to the transformed image. So what is the transformation function? S is equal to T of R, and it is given by the simple probability density function 0 to R PR of W. So ds, what is this differentiation value dr by ds? So we are differentiating the above expression with respect to R. So ds by dr equal to d of T of R by dr. So finally we get this L-1 into P of R. But in the original expression we have dr by ds. So taking reciprocal of this expression, P of R and PR of R will get cancelled. So we get only 1 by L-1. So what is this? Similarly we can take inverse. So finally if I want to have the value, we can take the inverse transformation. T of Rk is equal to, substituting in this, okay, L-1. So here we are actually substituting the value. Okay, PS of S value we are actually substituting. So PR of Rj is equal to L-1 into Nj divided by Mn. So we get this. So what is this? Is your applying transformation here. So this is your arbitrary PDF. A represents, and this B figure represents applying the transformation function with this equation 3.3.4. What is this equation? So by applying this transformation function S equal to T of R equal to L-1, by obtaining that we get this equation like this, normalized equation. So how the image will be? We are collecting the different gray levels. You see the histogram image is nothing but a graph, and x-axis represents the number of intensity values from 0 to white color. Okay, 0 represents black color. So in the graph also you see we have so many lines in the first side, but here in the last we don't have any lines. It means there is no white color in the image, so we have no lines in this dark image. And similarly you see the bright image, we have only white color, more amount of white color, so the graph moves to the right side. So in the first dark shade there is the intensity values are 0. So okay, low contrast image, we have some gray values only, no white or no black. So we have intermediate values. So if it is a high contrast image, what it means? All the intensity values are equally appear in the image. We have black color, we have white color, we have gray shades. So all the different values of intensity are equally appearing in the image. So it gives a very good effect to our eye. So it is an enhancement technique, equalized histogram. High contrast image is nothing but our histogram equalization. So that is the value actually what we are doing with the 64 cross 64 image. So this is our histogram equalization process. So this is the original histogram, that is zeroth intensity. The value of 0 intensity is appearing 0.20 times and the value of 1 intensity is appearing for 0.25 times. That is the meaning of this graph. Now we are taking the transformation function for this graph and we are plotting like this, and third one is the equalized histogram. So all the values are equally appearing in the image. So no particular black shades, not minimum image white shades. So okay, this 7 and all high intensity compared to the 0th value. So now we are all averaging all the lines to a near and then values. So we get a equalized histogram. So these are all the transformation functions. So histogram equalized image, that is a high contrast image, already we see it. And next process is histogram matching. So it automatically determines the transformation function and automatically determines. So but there we are transformation function we are fixing with certain conditions, but here there is no the equalization, the transformation function produce the histogram. But when automatic enhancement is needed, equalization is a good approach. But there are some applications which attempt to base enhancement on a uniform histogram is not the best approach. We are not using automatic means. In some particular times, we gives the shape of the histogram. Our image should looks like this. If I am specifically defining the histogram means, then I can match my specifications with the given image. So the method used to generate the processed image that has a specified histogram is called as histogram matching, or it is also called as histogram specification. And the algorithm or the procedures is like this. So S represents the transformed image and R represents the grayscales in the original image, and these are the functions we are using, and we have three steps here. Here also we are doing the mapping function. So that mapping function we are taking from the specified histogram, because I am the user, I want my image to be like this, so I am defining my histogram like this. So I want the real image to this mapped my specified histogram. So here I am mapping that my specified histogram values to the original image. So that is here. From the specified image, the equalizing inputs will be are mapped. So we get this. So this is the process of histogram matching. It is also the same as histogram equalization. The only thing in equalization, it is automatic transformation, but here if in certain applications, if the quality of the image is needed is very clearly defined, then we can also generate the image like that. So that case we can use this matching or specification. So okay, and the values are like this. Histogram matching is like this because we know the value, but here we are mapping that value to that mapped values. Okay, that is histogram matching, and the result is like this. Okay, so input intensity and histogram. This is the matching results. So here we have not all black, not all white. So here also it is spreaded like this. So here also we have local histogram processing. If it is applied to a particular mask size, then we can call it as a local histogram processing. But here generally for throughout the image, full image if you are applying, then we call that process to be global. So here also it is pixel to pixel, then it is global. But if each location the histogram points are computed in the neighborhood, then it is called local processing. So sometimes we need to have histogram only for a certain portions of the image, not for the whole image, then we can use this local histogram processing. So this is global histogram equalization, and the last one, it represents the local. In certain areas only we are going to apply the histogram. Okay, these are all the textbooks I have referred, and the Gonzalez book is having all the contents which I have used. All the figures are present in the Gonzalez book. Thank you.